2016 Christopher Heide Medal. The Christopher Heide Medal honours contributions to mathematics by Academy Fellow, the late Professor Christopher Heide. In 2016, it recognises outstanding achievements in pure mathematics. The recipient of the 2016 Christopher Heide Medal is Dr. Luke Bennetts. Luke, would you come forward?
Dr. Bennetts is an applied mathematician who models how waves of various kinds, example acoustic waves, electromagnetic waves, and waves at the surface of the ocean, are affected by solitary objects or assemblages of objects in their path. A major focus is on how ocean waves interact with ice flows in the polar seas, as this phenomenon appears to be a key contributor to the changes the Earth is experiencing in the Arctic basin and the Southern Ocean due to the onset and furtherance of global climate warming. Because the polar regions are so important to the world's atmosphere and oceans, the methodology that Dr. Bennetts has created is also immediately applicable to the refinement of hemispheric scale coupled operational climate forecasting as well as contemporary research schema. His fusion of analytical technical mathematics with sophisticated computational methods allows real-world problems, including nonlinear modes of behavior, to be tackled and solved. Dr. Bennetts, congratulations. I invite you to now to speak to us on ocean waves and sea ice.
Thank you. Yes, thank you very much to the Academy, and thank you also to all of my collaborators and mentors. I'm going to talk today about modelling interactions between ocean surface waves and sea ice. That is the frozen layer of seawater covering vast expanses of the high latitude oceans. As a science community, we can do very impressive things in terms of modelling waves and modelling sea ice. This video on your left-hand side was produced by the Bureau of Meteorology using a wave model. The image you can see on the right-hand side is a snapshot from a popular sea ice model. I'm interested in where these models overlap. We can certainly measure waves in the ice-covered ocean. It just takes a lot of time, money, and particularly effort. The photo at the top left of this slide is of a collaborator who collected the most comprehensive data set on waves in the ice-covered ocean. That was 3 years ago and in the Antarctic. She's pictured crouching next to a couple of the devices that she used, and in the photo beneath, you can see one of those devices deployed on an ice floe. Nature published her measurements, but the finding from the paper that has had the greatest impact came from a combination of a numerical model and satellite observations. The relevant figure from the paper is shown on the right-hand side of this slide. It shows that trends in the location of the Antarctic ice edge are closely correlated to trends in the local wave height. Where the waves are becoming stronger, the ice extent is shrinking, and vice versa. That relationship between waves and ice extent is attributed to the waves breaking up the ice cover, leaving it weaker, more mobile, and more susceptible to melt. Now, breakup is a very difficult thing to record in the Arctic or the Antarctic. The series of photos I'm about to show you come from the St. Lawrence Estuary in Quebec. The white is the sea ice. The grey on the left-hand side is open water. There are waves from the open water impacting on the ice cover. It's causing it to bend and flex and breaking it into smaller flows. The breakup only occurs in the vicinity of the edge because the ice damps the waves. And what we see is that over the course of minutes, the front of the broken ice is propagating deeper into the ice cover. Around 5 years ago, I was involved in a project to model that sort of event. I'm going to show you some snapshots of the model applied to the region of the Arctic known as the Fram Strait. The instant wave field is on the right, and the initial ice flow sizes are on the left. We set them to be large because we consider the ice to be unbroken at the beginning of the simulation. We then release the waves. On the right-hand side, you see that the waves are propagating into the ice-covered ocean, but the ice is damping the waves. On the left-hand side, you can see the breakup of the ice that's occurring where the waves have penetrated. So that's a large-scale numerical model. It has grid cells, which are approximately 5 kilometers long. Now, the model considers the ice cover to be a continuum. That's really the only reasonable thing to do from a computational standpoint. It means, though, that it doesn't resolve the individual flows. In a similar manner, it considers the wave fields to be an energy distribution rather than a collection of individual waves. What we want to do is find out the distribution of energy in the ice-covered ocean so that we can predict breakup. To do that, we need to consider processes occurring on a smaller scale where we do resolve the individual flows. The photo that you're seeing here shows a distribution of flow sizes ranging from a few meters up to perhaps 100 meters. Now, for the wave ice problem, there's another length scale to consider. That's the wavelength. The significant complicating factor is that the wavelength is comparable to the flow sizes. From a physical perspective, that means that the waves see each of the individual flows. From a mathematical perspective, it means that there's no small parameter available to homogenize the problem. Because of that, solving mathematical models of these sorts of problems inevitably involve a lot of hard work. It's necessary to consider each of the scales in the problem separately, from an individual flow to a group of tens to hundreds of flows, up to a full sea of flows. And we've developed efficient methods at each of these scales that then facilitate calculations at the subsequent scales. Having this computational efficiency is essential because we only know the inputs to the model, such as the distribution of flow sizes and the instant wave field, up to probability distributions. That means that what we're doing is we're extracting statistical quantities from ensembles of randomly generated realizations of the problem. The image at the top here is a model snapshot of a wave field traveling from left to right through a distribution of circular flows. The graphs beneath it show the way that the ice cover damps the wave energy and also how the ice cover spreads the directional spectrum of the wave field. Up until this point, I've only been talking about the problem in the horizontal plane, that is on the ocean surface. However, wave ice interactions are very much a three-dimensional problem, and the thinness of the ice drives some highly non-linear phenomena. I'm going to show you a short clip. It's of a simple laboratory wave tank experiment in which we used a plastic sheet to model an ice flow and subjected it to waves coming in from the right-hand side here. So notice in particular that the waves are washing over the surface of the flow, and that's extracting energy from the surrounding wave field. For my final slide, I just want to show you a mathematical model of the overwash phenomenon that we developed just recently. In particular, look for the fact that it recreates those bull waves that we see in the experiments in the overwash region. Okay, well, I've run out of time, but perhaps just a quick closing comment, which is that all the stuff that I've spoken about is just a small part of a much bigger multidisciplinary picture that's going on, but there's still lots and lots of good open problems available for applied mathematicians in there. Thank you.
Thank you, Luke. Are there any questions or comments?
Thank you for that summary of a very complex piece of work. In your multi-flow model, you allow for a flow size distribution. Do you also have an ice thickness distribution, or is it all uniform thickness ice?
Absolutely, it could be, you could have a thickness distribution. Typically, though, people stick to just a single thickness. I suppose there's not a great deal of knowledge about the thickness distribution in the same way that there is about the flow size distribution, and also there's some belief that the flow size distribution is perhaps a stronger controlling factor in these sorts of models, I hasten to add, not in general terms.
Luke, I'll ask the question you will expect me to ask. How useful would periodic models be for this problem?
Sorry, say that again, how do I?
How useful would periodic models rather than large-scale?
Well, as you well know, Ross, periodicity has a very strong effect on the wave field, and people have tried using periodic models for the wave ice application, as you well know, with mixed success. I think there's a case for using some periodicity in there for computational efficiency, but you've certainly got to put some form of perturbation in there to get rid of those resonances that it can drive.
Last question, John.
On the correspondence between the retreat and expansion of the ice edge and the wave activity, do you have a feel for which is the chicken and which is the egg?
There is a lot of debate going on about this. I've got to be a little bit careful what I say here. I mean, the proposition that I put forward in this talk sounds perfectly plausible, that you know, the waves are coming in, breaking up the ice cover and making it weaker, and that's driving some retreat of it, and of course the opposite can happen as well. Is it dominant? No, it's too early to say. It really is, and having sophisticated, accurate models is absolutely necessary in order to be able to answer that question.
On that note, could you please join me to thank Luke for a fascinating talk?